Hi, so in this video we will discuss NTA December 2019 questions solved for the sections of Statistics and Econometrics. So this was the most recent exam conducted and a total of 8 questions were asked in together from the sections of Statistics and Econometrics. So other than 1 or 2 questions like bootstrapping technique, it more or less covers our syllabus area itself. So we will discuss each of those questions one by one in this video. So moving on to the questions. The first question, match the test with their purpose. So we have a match the following question here. So we have list 1 and list 2. So it's Dickey-Fuller test, Box-Jenkins test, Glesger test and Granger test in list 1, and heteroscedasticity, causality, forecasting and stationarity in list 2. So we have to match each of the test with their particular phenomena. So choose the correct option and we have the following codes. So Dickey-Fuller test, as we know, is a test of stationarity. And other than Dickey-Fuller test, there is one more test which is unit root test that test stationarity. So A is definitely 4 and we have only one option with A as 4. So definitely 3 is the answer, but still we have to look into other tests as well. So option B is Box-Jenkins test. Box-Jenkins test is clearly a test of forecasting. So again B will be 3. B 3 is the option for third solution. And option C is Glesger test. Glesger test is a test for heteroscedasticity. There are also various other tests that is used to check heteroscedasticity. We will discuss that. And the last one is Granger test, and as the name suggests, it is a Granger causality test. So Granger test is again causality. So D is 2. So if we match all those, we got the answer even from the first option itself, but still if we match all those, we will get 3 as the option. So solution is 3. Dickey-Fuller test is stationarity, and another test used for stationarity is unit root test. Second is Box-Jenkins test is used for forecasting. Glesger test is used for heteroscedasticity and Granger test is used for causality. This is in the context of this question. So we will also look into the other test of heteroscedasticity. The other tests that are used for heteroscedasticity could be Park test, Spearman rank correlation, Goldfed quant test, Breusch-Pagan test, White test and Koyenker-Bassett test. These questions, these sections will mostly be asked for match the following, etc. So it's good to know the names of the persons associated with these tests so that you can match them easily. So that's about the question 1. Moving on to the next question. Analysis of variance is carried out by using option 1 t-test, z-test, chi-square test and f-test. So as we know from the primary understanding from sampling estimation or hypothesis testing, we know that t-test is used for small samples. Say sample size less than 30, t-test is used. For large samples, z-test is used, or it is the test used for normal distribution. Chi-square test is the goodness of fit, and f-test is nothing but Snedeker's F distribution, which is the analysis of variance. So clearly analysis of variance is carried out using f-test. Next question, we have an assertion reason question. So assertion states that geometric mean is theoretically considered as the best average to construct index numbers, and reason says geometric mean is used if the range of observation is very large. So option 1, if both are true and R is the correct explanation of A. Option 2, if A and R are true and R is not the correct explanation of A. Option 3, if A is true but R is false. And option 4, if A is false but R is true. So we have to look into this. So we already know the concept of geometric mean from descriptive statistics. So geometric mean is theoretically considered as the best average to construct index numbers. This is absolutely true. Geometric mean is directly applied to construct index numbers. So we know that assertion is true. And what was the reason? Geometric mean is used if the range of observations are extremely large. Say for example, we have a range of observation from 0, 5, 25, 100 and 150. In that case, if we apply arithmetic mean, the problem is arithmetic mean is basically taking the sum of the observations divided by number of observations. So these larger values will play a greater role in deciding the average. So in that case, taking arithmetic mean as the measure of central tendency will lead to false conclusions. So if the range of, because geometric mean is also the squares of data. So when you take the average, it is most likely to give the correct conclusion. So if the range of observations are extremely large, it is wise to use geometric mean. So we know for a fact that geometric mean is theoretically considered the best average to construct index numbers, as well as it is used if the range of observations are extremely large. But the problem is, both of these statements are true in the context of geometric mean, but one does not follow from the other, or one does not explain the other. So both are true, but it is not the explanation. So we will come back to the options. Both A and R are true, and R is the correct explanation of A. Both A and R are true, and R is not the correct explanation of A. So we will have to stick to option 2. It is not the correct explanation. So for the answer to this question will be option 2. Now the next question is, which of the following statements are true concerning a triangular or recursive system? Now about this question has been repeatedly asked since June 2012. So it's not more about the details of the question, it's just about the properties of triangular or recursive system. Whenever a question has been asked regarding this section, it's always asked in the same format. So there are few properties of triangular or recursive system, and it is always asked in statements question and which of them are true. So all we have to do is learn the properties of triangular or recursive system, and then we will come back to this question. So triangular or recursive system, the three primary properties of such a system is, the parameters can be validly estimated using separate application of OLS to each equation. So in a triangular or recursive system, how do you estimate the values? The parameters can be validly estimated by applying a separate OLS to each equation. To each equation you apply a separate OLS. Second is, the independent variables may be correlated with the error term in the equation. So the independent variables in the model could be correlated with the error term in that equation. That is another property. The final property is, the application of two-stage least squares would lead to unbiased but inefficient parameter of estimation. When you apply two-stage least squares, it would lead to unbiased estimator, but the estimator would still be inefficient. So these are the three properties of triangular or recursive system. Now that we know these properties, let's come back to the question. So the question says, option A, the parameters can be validly estimated using separate applications of OLS to each equation. We just saw that we can do that. So to each equation you can apply a separate OLS, and then you can estimate the equation. So that is absolutely true. Secondly, the independent variables may be correlated with the error terms in other equation. That is also true. The independent variables in the equation could be correlated with the error terms in the equation. So option A and B is true. Coming to the third one, the application of two-stage least squares would lead to unbiased but inefficient parameter estimation. This is the benefit of learning from this section, because the words will be used as exactly as is in the properties. So you can just cross check and find your answer. So like we just said, when you apply a two-stage least square method to a triangular or recursive system, you get an unbiased estimator, but still the estimator would be inefficient. So A, B and C is true. What's the fourth one? The independent variables may be correlated with the error terms of the equation. That much is as repetitive as the second option, in which they appear to be independent variables. That part is not true. So we cancel out D. A, B and C are correct statements. So choose the correct option, A and D, A and C, A, B and C, A, B, C and D. So we cannot choose D. So A, B and C only. Option 3 is the correct answer. So that's about triangular or recursive system. The next question that was asked was, there are three statements are given as under. One is, generalized least square or GLS method is capable of providing blue in situations where OLS fails. GLS is OLS on the transformed variables that satisfy the standard least square assumptions. GLS method is suitable for dealing with multicollinearity problem. Again we'll discuss what is GLS. GLS is basically generalized least squares. So what does that actually mean? It is basically generalization of the OLS. The usual method used in a regression model is ordinary least square using the least square principle. So GLS is basically generalization of the OLS method. It is capable of providing blue in situations where OLS fails, that is when the assumptions of homoscedasticity and absence of serial correlation fails. So what do you mean by this statement? In a classical linear regression model, there are certain assumptions that hold the model together. One of them is homoscedasticity and one of them is there is no serial correlation, that is there are no correlation or dependence between the error terms. So those are the primary assumptions of classical linear regression model. We have already discussed that in the sections related to that. So what they are trying to say here is the GLS is capable of providing blue. So what is blue again? This again is a concept we discussed in classical linear regression model. Blue is best linear unbiased estimator. So applying a GLS method, we can still get blue even when OLS fails. So even when homoscedasticity and absence of serial correlation fails, we can still get a blue estimator by applying GLS instead of OLS. That's the point being made here. And GLS is actually OLS on the transformed variables that satisfy the standard least square criterion, and it is suitable for dealing with heteroscedasticity and autocorrelation. So these are the limitations of classical linear regression model when you apply OLS. You cannot do if there is no homoscedasticity, and you cannot do if there is autocorrelation. So in all these situations GLS could be applied. So coming back to the question, generalized least square method is capable of providing blue in situations where OLS fails. So this is true, we just saw that. And again GLS is OLS on the transformed variable that satisfy the standard least square criterion. That is also true. GLS method is suitable for dealing with multicollinearity problem. That's not true. We just discussed that GLS method is suitable for dealing with homoscedasticity, heteroscedasticity. GLS method is suitable for dealing with heteroscedasticity and autocorrelation, but not multicollinearity. So we have A and B is true, but C is not true. So A and B are correct, C is not correct. A and C are correct, B is not correct. A is correct, but B and C are not correct. A is not correct, but B and C are correct. So we have option 1 as the answer. A and B is true, but C is not true. Now the next question. For an exactly identified equation, the order condition that should be fulfilled is that the equation must, option 1, exclude 1 less than the total number of endogenous variables in the model, 2, include 1 less than the total number of endogenous variables in the model, 3 is include only one of the endogenous variables in the model, and finally exclude 2 or more endogenous variables. So what exactly is a simultaneous equation model? Unlike single equation model, there is a relationship from both sides. There existed two-way relationship between the variables. X is related to y as well as y is related to x. So unlike single equation model, there existed two-way relationship in simultaneous equation model, and there are two main conditions for order condition. So those two conditions are: 1, in a model of m simultaneous equations, in order for an equation to be exactly identified, it must exclude exactly m minus 1 variables. So it's saying in a model of m simultaneous equations, for an equation to be exactly identified, it must exclude exactly m minus 1 variables. And the second condition is, in a model of m simultaneous equations, in order for an equation to be exactly identified, the number of predetermined variables excluded from the equation must be equal to the number of endogenous variables included in that equation less 1. So from these properties directly we can say that we should exclude 1 less than the total number of endogenous variables in the model, should be m minus 1. For an exactly identified equation, the order condition should be fulfilled such that the equation must exclude 1 less than the total number of endogenous variables in the model. So this is option 1 is the answer. Next question. Under a normal probability curve, the area within the range of mu minus 1.96 sigma and mu plus 1.96 sigma, where mu is the mean and sigma is the standard deviation. What is the area? So in a normal distribution curve, we know that within a range of mu minus 1.96 sigma and mu plus 1.96 sigma, the area covered is 95%. The total, as we know the properties of normal probability curve or a normal distribution, it is symmetrical, it's bell shaped, and the total probability is 1. The area under the normal probability curve is in together 1. But in between mu minus 1.96 sigma and mu plus 1.96 sigma, the area covered will be 95%. So option 2 is the answer. And now this is the new concept. All these other areas that we discussed were already somehow covered in the syllabus area. This is a totally new concept that was asked in this exam. Bootstrapping technique. It is used to, for which of the following? Test for specification bias, obtain sampling distribution of parameters of interest, test for autocorrelation, or test for normality of error terms. So for which of the following bootstrapping technique is used for, or what exactly is bootstrapping technique? So let's see that. So the bootstrap method is actually a statistical technique for estimating quantities about population by averaging estimates from multiple small data samples. So this is an idea that we already are familiar with. To identify something from a population, we take a sample from a population and we study on that. That's how we make estimates, or that's how we make ideas about how the population is going to behave. So it is a statistical technique, alright, for estimating quantities about a population by averaging the estimates from multiple data samples. With regard to these data samples, now how do they choose? In a bootstrap technique, we take samples from a population and we study about the population. Now how do we choose these samples? It is chosen via random sampling with replacement. So for some refresh to the memory, what is random sampling with replacement? When a sample is drawn from a population and after noting its particular characteristic, if it is returned to the population before the next unit is drawn, it is referred to as random sampling with replacement. From a sample, from a population, you take a sample, you study what it is about, and then you put it back, and then you take the next sample. That's basically what is meant by random sampling with replacement. So in a bootstrapping technique, when you take a sample from a population, you rely on this method. You actually replace the data sample that you took to study. So this method actually assigns measures of accuracy defined in terms of bias, variance, confidence intervals, prediction error, or some other measure to the sample estimates. And this technique allows the estimation of the sampling distribution of almost any statistic using random sampling methods. So we can say that from these observations or from these options, the idea behind the bootstrapping technique is to obtain the sampling distribution of the parameters of interest. It is to obtain the sampling distribution, and it has nothing to do with specification bias or autocorrelation or normality of error terms. So we now know that bootstrapping technique is used for that. So what are the other options used for? So moving on to that, option 1 is specification bias. Yeah. So what is specification bias or error in a regression model? How can it happen? So either it could be due to leaving out some important explanatory or independent variables from the model, or including unnecessary variables to it. So you leave out something important or you add something unimportant. That could be one reason of specification error. Or if you choose a wrong functional form between the independent and dependent variable. So whatever the functional form is between independent and dependent variable, you choose something else. So when you choose a wrong functional form, it could lead to specification bias or error. So in the case of a specification error, it is not bootstrapping technique that is used, it is Ramsey reset test or regression equation specification error test. That's the full form of reset test. So that is the test that is used for linear regression model. It is used to check if the nonlinear combinations of the independent variable have any power in explaining the dependent variable. So that's about specification error. These are the reasons how it can happen, and this is the test used for finding out specification error. The next option, option 3, was autocorrelation. So autocorrelation is basically the correlation between members of series of observations ordered in time, as in time series data, or in space, cross-sectional data. So as per regression context, the classical linear regression model assumes that there is no such autocorrelation that exists between the disturbances or the error terms ui. So if at all there is, or if you want to check the autocorrelation, which test do we use? The most prominent test used for autocorrelation is Durbin-Watson statistic. Is the most commonly used test for autocorrelation and not bootstrapping technique. Next, option 4 was normality. So to test for the normality of error or disturbance terms, which test do we use? Kolmogorov-Smirnov test or Jarque-Barra test could be used. See, these are the two tests for normality of error or disturbance terms, Kolmogorov-Smirnov test or Jarque-Barra test. So these are the tests used for normality of error terms. So with that we have explained all the options under bootstrapping technique. So that is clear. Now moving on to the last question that was asked in this question paper. In terms of their contribution to econometrics, which is the correct chronological order? So we have a set of economists or econometricians who have contributed to this discipline. So what is the correct order of them contributing? So in all these options we have Klein, Thale, A.L. Nagar and T. Havelmo. So who came first? What did they contribute? So there is a reason why these people are put together. All of them have somehow contributed to the simultaneous equations or structural equations, that arena of econometrics. That is why this question is asked for these 4 people, because their contributions have somehow linked with each other. So when you look at it, Havelmo is the first one who brought out some contributions to simultaneous structures. Among these 4 people, he was the first one. So that happened in 1943. So that is when Havelmo introduced some new ideas to simultaneous structures. And following in the same year, but following up on the work of Havelmo, was L.R. Klein. He further developed the identification in simultaneous equation models. So both of them happened in 1943 itself, but L.R. Klein actually was working on the follow up of Havelmo. He was actually following up on Havelmo's work. Thirdly, Thale. He was working on two-stage least-squares in 1953. And finally, A.L. Nagar was working on the sampling properties of simultaneous equations in 1959. So all these areas somehow are connected with each other. These 2 people are directly connected because he was following up on his work. So Havelmo started with the ideas on simultaneous structures in 1943. Later that year, L.R. Klein was following up on the work on Havelmo on identification of simultaneous equation models, followed by H. Thale in 1953 on two-stage least squares, and finally A.L. Nagar was working on the sampling properties of simultaneous equations in 1959. So we have 2 in 1943, early in 1943, later in 1943, 1953 and 1959. So following on that order, we have Havelmo, then Klein, and then Thale, and finally A.L. Nagar. So option 3 is the answer. So this comes to the conclusion of this video. We have discussed all the questions, all the 8 questions that were asked in the section of statistics and econometrics for 2019 December NTA exam. So yeah.
Hope you enjoyed the video. If you are a NET aspirant and want to crack UGC NET, our helping hands are there for you. Our systematic pattern of teaching helps you to achieve your dream career. By subscribing our premium package, you will be offered with simplified notes, video lectures, PPTs and model text papers in exact software of NTA examination. We also offer online packages for economics, commerce, management, English and various other subjects, combo offer which covers online coaching for respective subjects and general paper, and add-on packages including printed study materials. So, if you want to redefine your capabilities, Appleby is your clear choice.